We'll try and make up that time. So Francisco can't be with us this morning, so I'm going to take care of his part as well. This is sort of stretching the topic of repair a little bit here, but we've applied new or larger standardized GFRP reinforcing bars for an application on this particular bridge where scour, riverine scour, has compromised the integrity of the end of the bridge, the last three end vents that you can't see there. It's in North Florida. Oh, let me back up. So this is one of only two rapids in Florida. Pretty level state. I didn't even know that this existed, but a little south of the bridge there's a small section of rapids under high flow rates. But the actual location of the bridge is near a bend in the river, and so the velocity of the flow scours out the last three pile bents. And so part of the mitigation for that was to provide a what we call a crutch bent, which is basically a new, usually a larger pile bent that has piles installed outside the footprint of the bridge because you can't really get driving equipment in, and it's either installed on either side of the existing cap, or in this case it was encapsulating the existing cap. And so the proposed design was post-tensioned, so it had four tendons, and the contractor wasn't very keen on mobilizing and doing the post-tensioning under a subcontractor, so they wanted to self-perform the work with a reinforced system. And so in this case, we wouldn't normally allow steel reinforcing for this type of element, but with the adoption of GFRP, the cracks are not necessarily a corrosion or a durability concern, and so the contractor in this case proposed a system to replace the existing EOR engineer of records design with the post-tensioning. So they took on all the design responsibility and also had an independent peer review, plus we looked at the design as well. And so this in yellow is the existing cap, and then you can see this massive beam, which is basically a 5x5 concrete beam with larger piles, concrete piles driven on either side. And in the next slide you'll see it's fairly congested in the bottom, mainly because of the contractor's engineer did not want to change the footprint. That would have invoked a whole bunch of other hydraulic issues with the size of the cap. And so maintaining the existing 56-inch, 60-inch width and 63-inch depth, they were able to traverse the existing piles and the new piles with originally there was 40 number 11 bars that were used in this design. They were able to, with some fancy math, get it down to 36. Service control strength is not the governing limit state for this design, but so part of the existing options for design with GFRP under existing ACI and ASTM standards tap out at number 10 bars, which would have been more than double what you see there, which would be impractical. We do have a limit in Florida that we don't allow more than 4 rows of reinforcing in our caps and hammerheads and pile caps. And so this seemed like an optimal solution if they could get the design to work. And so this was modeled in FB multi-pier, nonlinear soil interaction analysis, plus the design of the cap itself was also done with independent MathCAD design, following the AASHTO GFRP guide specifications for bridge design, which is very similar to 440, since Professor Nani helped us develop those. So the use of number 11 bars was implemented last year in the DOT specification. It's not currently in the ASTM. So manufacturers have been making these bars and larger for quite a while for temporary applications in tunneling and soft eyes and other things. So we knew that there was the availability in the market. We also knew that as we progress from bridge decks and other smaller structural members, that larger bars are going to be needed. Pretty much every pile cap footing that we design in steel uses number 11 bars. Any hammerhead cap will use 11s, maybe 14s. And so our motivation in Florida is to use these materials for substructures, because that's where we have our corrosion problems with the marine environments and salt water. So that was really the motivation for pushing the adoption of larger bar sizes. This research, which Francisco did most of the heavy lifting on, Dr. Nani was the lead on that one. It is really part of the support for the ASTM ballot that's currently out for adding number 11 bars. We feel, or I feel, there's room to add, or a need to add larger bars as well. So maybe not all the way up to number 14 yet. I mean, FRP is a little more flexible, so number 12s and number 13 bars are pretty common from some European producers and Canadians. So that's probably where we'll go next. But part of this study was to see if we guessed the right numbers in our specification. And if you're familiar with the current two ASTMs that specify mechanical properties for FRP, GFRP, and BFRP bars under D7957 and 8505, they are two separate elastic modulus for tensile stiffness, and so our target was to hit both of those with the number 11 bars. Optimally, the higher 8505 limit of 8700 KSI, it's an MSI here, so which is 60 GPa in metric speak. So we got there with one manufacturer. We were pretty close with the other. So the decision now is, do we lower the modulus and make it even more complicated in design, or do we ask the manufacturers to cram more fibers in there, or allow them to go slightly oversized on the bars, more than we already do? And so these are decisions that really affect 8505, not 7957, because that's pretty easy to achieve the 45 MPa, 6500 KSI stiffness. On the strength side, we're way over the extrapolated strengths of the existing bar sizes. So we've got, where's my time to? We've got a limit right now that we proposed 160 kips for the strength of a number 11 bar. I think that's pretty much what Francisco's balloted for the ASTM. You can see from these test results we are well over that, twice that, or not twice that, but we are well over the 160 kips. So 185 with one, 200 and wherever it is, 247 there, which is way over. So there's some unused potential there, I think. We have a third manufacturer, I think he's sitting in the room, that offered to provide their bars, but we didn't have the money for this project. But as we approve manufacturers for these larger bars, then they'll have to do the full suite of testing anyway, so we'll get that information. But so that's sort of it's a practical implication of existing technology, just standardizing for broader adoption. As far as comparison to what the steel reinforced design would have given us, grade 60 anyway. So that yield strength on those bars is around 94 kips. So you can see we're twice the strength, 2.5 times. Throw in the environmental reduction factors and the lower resistance factors for flexure, you're still stronger, just not as much, but pretty much every case service limit states will control, and that's mostly governed by stiffness. And so we will still need more reinforcing, but perhaps not as much, depending on what limits we put, upper limits we put on the strength. And so just the example of the scatter in the data, which there was not much on the stiffness for these bars. As part of the research project, we did a couple of design comparisons to existing designs for, in this case, it was a pile cap at the waterline footing. And so those were proved to be very achievable. Did highlight some issues challenges we will have with shear, because if you're just using one-way flexural analysis for the diaphragm, for the pile cap, then you end up not quite meeting the shear limits. So what we do with that is being investigated under some other projects. So there's some conservatism in the design for shear that I think this project has proven that we're either got to start adding shear stirrups to our footings, or change the rules. So that's what the plan is moving forward. Appreciate all the work that our partners at UM and the manufacturers, and we always close with a safety message, Flora, so no texting while driving. I know it's difficult not to. And so I think I left some time for questions.
Absolutely.
Yeah.
Welcome.